Hello students, let's continue with number system. Until last class we completed question 4 of exercise 1.3. Now let us continue with the remaining sums. So we are on question 5 of exercise 1.3 on page 14. Let's read the question. What can the maximum number of digits be in the repeating blocks of digits in the decimal expansion of 1 upon 17? Perform the division to check your answer. Now before I proceed with solving this question, we know that the maximum number of digits in the repeating blocks of digits in the quotient of a decimal expansion of rational number is always less than the divisor. Right? So the maximum number of digits in the repeating blocks of digits in the quotient of a decimal expansion of a rational number is always less than that of the divisor. So here my divisor is 17. My fraction is 1 upon 17. So 17 is my divisor, right? Now as per this, the maximum number of digits in the repeating blocks of digits of this quotient of the quotient of this rational number will be less than 17, right? Will be less than 17 repeating blocks. Right? So one number less than 17 is 16. So we need to check whether the repeating blocks in the quotient of this fraction is going to give me 16 or less than that. Okay? So let us go ahead and verify. I have erased the chapter's name because this is going to be a pretty long sum. Let me write the question 1 upon 17. So 1 is my dividend and 17 is my divisor, which is why 1 goes inside and 17 goes outside. Right? Now let's check. 17 zeros are 0 because 17 cannot divide 1, right? So I have 1 here. Now I need to find the recurring decimals, which is why I am going to add a decimal point here in the dividend as well as next to the quotient, and I will add many zeros. So now I bring down this 0, 17 zeros are, and I am left with 10, right? I bring down this 0 and let's check what is closest that will go in 100 for 17. So 17 5s are, so 5 7s are 35, 5 1s are 5, 6 7 8, 85. Let's check for 17 6s are. I have 17 6s are, 7 6s are 42, 6 1s are 6, 102. So not 102, I will take 17 5s are 85. So 100 minus 85 is 15. I bring down this 0. Let's check for a term closer to this. 17 into 7. 7 7s are 49. 7 1s are 7. 8 9 10 11 119. How about 17 8s are? 17 8s. 8 7s are 56. 8 1s are 8. 9 10 136. So 17 8s are. Let's check for 17 into 9. 9 7s are 63. 9 1s are 9. 10 153. So I will take 17 8s are 136. So this will be 4 and 1, 1 4. I bring down this 0. Let's check for a term which is closer to this. Again I will take 17 8s are 136. I am left with a 4 over here. Now you will see that 8 has repeated twice, but this doesn't imply that 8 is going to be recurring. Always when you have one term repeating more than once or twice or thrice, just go ahead and solve a little more further to confirm whether the term is repeating forever. Okay, so I am going to go ahead and divide further. Let's take down this 0. I have 17 2s are 2 7s are 14, 2 1s are 2, 34, and 17 3s are 3 7s are 21, 3 1s are 3, 4 5. So 51. I'll take 17 2s are 34. So 40 minus 34 is going to give me a 6. Again I bring down this 0. Now what is close? We have 17 3s are 51. So 60 minus 51 will give me 9, and I'll bring down this 0. 17 5s are 85. 90 minus 85 will give me 5. I will bring down this 0 as well. 50. So we have 17 2s are 34. Let's check. We have 6 and 1. I'll bring down this 0. Now what is close? We have 17 9s are 153. So 160 minus 153 is 7. We haven't got any repetitive pattern of the quotient, the digits in the quotient. So I will add more zeros in my dividend. Let's bring down this 0. What is close? 153, then how about 17 4s? Have we calculated 17 into 4? Let's check 17 4s. 4 7s are 28, 4 1s are 4, 5 6. So 17 4s are 68. 70 minus 68 is going to give me 2. I'll bring down this 0. 20. So 17 1s are 17. 20 minus 17 is 3. Right? I'll bring down this 0. 17 1s are 17. So this is going to be 3 and 1 3. Let's bring down this 0. 130. Now what is close to 130? We have 8, 7, okay, how about 7? 17 7s are 119. You get 1, 1 and 0. What is close to 110? We have 17 6s are 102. So this is going to be 8. Now 17 5s was 85, so 5 won't go. Let's check for 4. 17 4s are 68. What am I left with? 2 and 1, 12. Now I do not have much space, so I am going to erase this section and continue my sum over here. So we had 1.000000000000. Okay. Do not take into consideration these number of zeros over here. Always refer to these. I am just writing it because we have to continue with the sum. So 17 is outside, dot dot dot, and we got a 12. And here our number was 0006764. So let's get down this 0. Now 17, what is close to 120? 17 5s are 17 6s are. Let's check. 17 7s are 7 sevens are 49, 7 ones are 7, 8, 9, 10, 11, so 119. We have 17 sevens are 119 minus 1. Then you get down this 0, 17 zeros are I get down this 0. So this pattern is repeating if you see. See, we had a remainder 1, then we had a remainder 10. Similarly, I got down this 0, but here was my remainder 1 and remainder 10. So you notice that this block or this entire pattern is going to repeat once again. Therefore, I'll just write my quotient here once, 76470. Right? So my quotient is 0.058823529417647. Okay? So I'm just going to write my quotient over here and we will count. The quotient is 0.00588233529 524 94 11 76470. So let me just confirm 0588 2352 2352 49 2352 9411. So 529411 76470. Let me just confirm once again. It's a huge number, so it's just going to take me time to confirm right here and there. 0.0588 2352 9411 76470. Okay, so here is my quotient when I divide 1 by 17, right? So let us count the number of digits that we've got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and I do not have to take this 0 because it was the repeating pattern. So not this 0. Why not this 0? Because I already have my 0 over here. I just wrote that 0 initially because that was to mention that the entire pattern from 0 is going to repeat, right? So my actual quotient that I have is 0588235294117647. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. So you will see that this entire pattern is going to repeat. Therefore, my quotient is a bar on top of this series of number. Now 16 is less than 17, where 17 is your divisor, right? Hence, what have we proved? That the number of digits in the repeating blocks of digits of your in the decimal expansion of 1 upon 17 is less than the divisor, which is 17, and our number is 16 over here, right? So let us write your answer. So the answer is actually over here. The maximum, should I just erase that section and write the answer there, or I'll erase the quotient? No, we don't need it right now to give the answer. Or if for the quotient you can take a reference, I'll write it here for you. This is your quotient. Okay, so let us write the answer because we want to mention what the answer is. What can the maximum number of digits be? So the maximum number of digits in the repeating blocks of digits of decimal expansion of 1 upon 17 is 16. Okay, and after that you can just write your quotient. Quotient is equal to you, whatever answer you have. I'm not writing it for you, you have the quotient right there. Okay? And to perform the division to check your answer, we have already performed the division to check our answer. Okay? So, should we go ahead and solve the second question, which is the sixth question of 1.3. Okay? So, let us see our question. Look at several examples of rational numbers in the form of p upon q, where q is not equal to 0 and p and q are integers with no common factors other than 1, having terminating decimal representations or expansions. Can you guess what property q must satisfy? So, we had looked at decimal expansion of rational and irrational numbers. We know that the decimal is terminating only in case of rational numbers. Now, did you notice when we solved examples that the decimal terminates only when the divisor, that is the denominator in your rational fraction, which is q over here, because we have it in the form p upon q, where q is either 2 or 5. Only when q is 2 or 5 will the decimal expansion terminate. Otherwise, it will be a recurring decimal number, right? So, let us take few examples. So, now we have to take two terms p and q such that both are integers and there are no common factors between them except for 1. So, I am going to take numbers in such a way, the numerator and denominator, such that there is nothing common between them except for 1. That is the factor, right? So, let us take for example 3 upon 2. Both are prime numbers, nothing common between them except for the factor 1, right? So, this can be written as what? 3 upon 2. Okay. Now, I need to convert this to a decimal form. I can either divide, okay, like this, 3, 2. So, 2 ones are 2 minus 1. I put a 0 here after a decimal. I bring down the 0 and I have 2 5s are 10, right. So, I get 1.5, or a simple way would be, a very simple way would be to convert the denominator into tens, hundreds, thousands. So, what will I multiply with 2 in order to get a 10, 100 or 1000? Let us see, the closest one that I see is 10. So, I multiply this by 10. Obviously, if I am multiplying the denominator, I am multiplying it by 5 to get a 10. So, obviously, if I am multiplying my denominator, I have to multiply the numerator in order to make sure that a fraction, the value of a fraction remains the same, right. So, I will multiply the numerator as well with 5. So, what do I get? I get 3 5s are 15 and 2 5s are 10. Now, see, finding the value of this is much more simple as compared to going through the entire process of division. Okay. So, I have 1 0 in my denominator after 1. Therefore, I will go back from my right hand side to the left hand side and place the decimal point between them. This is equal to 1.5, right. So, my denominator here was 2 raised to the power of 1, right. Let us take another example. I will take 5 upon, I will take 1 upon 5, okay. So, what will I multiply with 5 in order to make it in this form? 10 hundreds. The closest one is a 2-digit number, which is 10, right. So, I will multiply the numerator and denominator with 2. So, what do I get? 1 into 2 upon 5 into 2. So, what do I get? 2 upon 10, correct. So, now 2 upon 10 is equivalent to 0.2. Here my denominator is 5 raised to the power of 1. Now, let us take something that is 2 raised to the power of 2 and 5 raised to the power of 2 in our denominators. So, what number can I take? Let us say I take 7 upon 8. So, there is no common factor between these two numbers except for 1. Now, what will I multiply 8 with in order to get 10, right? So, let us check for 8 into what will give me 1000. 8 ones are 8, 9, 10, 8 twos are 16, 8 fives are 40. So, I will multiply my numerator and denominator with 125. Now, why did I do this division? Because I wanted to make 8 in the form of tens, hundreds, thousands. Obviously we know that 8 doesn't completely divide 100. So I went for the next slot, which was 1000, and I checked whether 8 is dividing, and I take my quotient. So when I multiply 8 with 125, I get 1000. Okay. So I am going to rewrite this as 7 into 1000, 7 into 125 upon 8 into 125, right? Because 8 into 125 is going to give me 1000, not 8 into 1000. That's why not 1000 but 125. So let's calculate 7 into 125. 7 5s are 35, 7 2s are 14, 15, 16, 17, 7 1s are 7, 8. So I get 875 upon 1000. So how many decimal places? There are 3 zeros here. So 3 decimal places from the back, 1, 2 and 3. My decimal point comes here. So this answer is 0.875. So you see that my decimal point, the terms after my decimal points are terminating. Now here my denominator was 2 raised to 3. So 2 to the power of 3, right? Let's go for another term. 8 upon 125. Okay. So 125 into what will give me something similar to 1000 or more than that, right? But it should be either tens, 100,000, 10,000. So let's check. We checked in this sum that 125 into 8 gives me 1000. So I am going to multiply and divide the this fraction by 8. 125, 8 into 8 and 125 into 8. So 8 8s are 64 and I get 1000. So 3 zeros, therefore 3 decimals backwards. So I get 0.064, right? This is again a terminating decimal with my denominator is equal to 5 cube. We know that 5 cube is 125. Let's take a look at another example. We have 13 upon what number can I take? 20. So you see that 20 is a multiple of 5 and 10 and 2, right? So what do I now? Closest 20 will divide 100. How? So 25s is going to give me 100. So 13 upon 20 into 5 into 5. So 13 5s we know it is 65 and this is 100. So this is 2 decimal places, therefore 0.65, and my denominator is 2 into 4 5s are 20, 4 into 5, which is nothing but 2 square into 5 raised to the power of 1. So we notice that the denominator is either 2 or power of 2 or 5 or power of 5 or a combination of both. So let us go back to our question. Let's read it. Can you guess what property must Q satisfy? So we notice that the prime factor of Q of the denominator should either be 2 or 5 or powers of 2 and 5 or a combination of 2 and 5. Okay, and this is to prove the answer. So let us just write our answer. I do not have space here, so I will just erase this section. Please take a look before I erase it. Okay. So answer, Q must either be 2 or 5 or power of 2 or 5 or combination of 2 and 5 in order for the decimal term to be terminating, or in order for the decimal to terminate, right? Q is the denominator. So we have solved question numbers 5 and 6 of your exercise 1.3. We will proceed with the remaining questions in our next class. Thank you.
Hope this video increased your knowledge. For more such videos and a completely free educational content, log on to www.epathshala.org or visit our ePathshala YouTube channel. We have each and every question solved for maths, physics, chemistry and biology. So subscribe our channel, share with your friends, like our Facebook page and follow our Twitter handle for regular updates and important educational tips, and also win ePathshala goodies. So what are you waiting for? Subscribe this channel and enjoy the freedom of education.